Tonight, we're going to take a closer look at our nearest stellar neighbor. Astronomers have pointed every serious telescope ever built at this system for generations. And after all those decades of searching, it has given us almost nothing back. Until now. Because when the James Webb Space Telescope turned its mirrors toward Alpha Centauri A, what the team found didn't fit what anyone expected. A planet appeared in the data, a Saturn-mass world, orbiting the larger of the system's two sun-like stars. And then, during follow-up observations, it vanished. By the end of tonight, you're going to understand why a planet could appear and then vanish, what that tells us about the limits of even our best telescopes, and why the answer could reshape how we search for worlds everywhere else. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Alpha Centauri isn't a single star. Most people assume it is a bright point of light in the southern sky, the closest star to our sun, a name that shows up in virtually every serious conversation about interstellar travel. But it's actually three stars, bound together by gravity into a system that has been quietly burning about 4.37 light-years away from us for billions of years. That's roughly 25.6 trillion miles. In cosmic terms, that genuinely is next door. The Milky Way is 100,000 light-years across, and on that scale, the gap between Alpha Centauri and our own solar system is barely a rounding error. But in human terms, it's still an almost incomprehensible distance. Light itself, the fastest thing in the universe, traveling at roughly 186,000 miles per second, takes 4 years and roughly 4 months to make the crossing from Alpha Centauri to Earth. That means if you sent a radio signal to the Alpha Centauri system right now, you'd wait over 4 years for it to arrive, and another 4 years for any response to come back. A signal sent today wouldn't reach Alpha Centauri until sometime in the early 2030s. By that measure, Alpha Centauri is our closest astronomical neighbor, and it's still separated from us by a gulf that makes any form of communication feel almost impossibly slow. The two main stars in the system are Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is a sun-like star, actually slightly larger and brighter than our own sun, with about 1.1 times the sun's mass and roughly 1.5 times its luminosity. It's classified as a G-type main sequence star, the same stellar category as our sun, though slightly more massive and slightly hotter. Its surface temperature runs around 5,517 degrees Celsius, or 9,962 degrees Fahrenheit, almost identical to our own sun. A difference so small, it's essentially negligible in terms of the light and heat the star produces. Alpha Centauri B is a bit smaller and cooler, sitting at about 90% of the sun's mass and about half its luminosity. It's classified as a K-type star. K sits just below G on the stellar classification sequence, representing stars that are cooler and slightly more orange in color. Alpha Centauri B's surface temperature is around 4,987 degrees Celsius, or 9,008 degrees Fahrenheit, noticeably cooler than Alpha Centauri A and our sun. Its light is more orange and amber than our sun's. And because it gives off less light overall, a planet would need to orbit closer to it than Earth orbits the sun just to receive the same amount of heat. These two stars orbit each other in an elliptical path that takes roughly 80 years to complete one full cycle. At their closest in their orbital cycle, they're about 11 astronomical units, apart roughly the distance from our Sun to Saturn. At their farthest, they stretch out to about 36 astronomical units beyond Neptune's orbital distance from our Sun. This variable separation has profound consequences for any planets trying to maintain stable orbits around either star. The gravitational tug of the companion changes considerably as the binary orbit progresses, and planets sitting near the outer edge of what's dynamically stable would experience periodically varying perturbations over the course of the 80-year binary cycle. The third member of the system is Proxima Centauri, a small red dwarf orbiting the other two at an enormous distance, currently about 13,000 astronomical units out, in a very wide orbit that takes roughly 550,000 years to complete. Some astronomers have questioned whether Proxima is truly gravitationally bound to the system or just a passing stellar neighbor that happens to be moving in roughly the same direction. Current measurements favor it being a genuine member. The three-dimensional velocities are consistent with gravitational binding, but its distance from Alpha Centauri A and B is so vast that the binding is extremely loose. Proxima is the star you hear about most often in exoplanet discussions now, primarily because of the planet discovered orbiting it. In 2016, a roughly Earth-mass world sitting in the star's habitable zone. But Proxima is not the star that James Webb was watching when things got strange. Webb was watching Alpha Centauri A. To understand why this detection matters and why the disappearance matters even more, you need to understand what it actually takes to find a planet around Alpha Centauri A specifically. This system has been one of the most frustrating targets in the entire history of planet hunting. That might sound counterintuitive. Alpha Centauri is the closest star system to Earth. If there were planets there, shouldn't we have found them already? We've found planets around stars hundreds of light years away. We've found planets around stars so faint they're invisible to the naked eye. How is it possible that the system practically next door has kept its planetary secrets hidden for so long? The answer reveals something fundamental about the difference between proximity and observational accessibility in astronomy. Being close doesn't automatically make something easy to study. In some cases, and Alpha Centauri is a clear example, proximity makes certain kinds of study actually harder. The most widely used planet detection method of the past 2 decades is the transit technique. A planet passes in front of its host star from our line of sight. The star dims by a tiny fraction of a percent, a few hundredths of a percent for an Earth-sized planet, a few percent for a large Jupiter-mass world. You measure that brightness dip, watch for it to repeat on a consistent schedule, and eventually confirm that a planet is crossing the star's face on a regular orbital period. This method found thousands of planets for the Kepler Space Telescope, but it requires precise geometry. The planet's orbital plane has to be nearly edge-on from Earth's perspective. Only a small fraction of planetary systems happen to be aligned this way when viewed from our location in space. For much of the Alpha Centauri system's orbital parameter space, the geometry is unfavorable. Then there's the radial velocity method, the technique that dominated planet hunting before the transit era came into full swing. Radial velocity works by measuring the Doppler shift in a star's spectral lines. When a planet orbits a star, the planet's gravity pulls the star in the same direction as the planet's motion, causing the star to wobble back and forth. When the star moves toward us, its light is compressed toward shorter, bluer wavelengths. When it moves away, the light is stretched toward longer, redder wavelengths. By measuring these tiny shifts in wavelength, astronomers can infer the presence of an orbiting planet from the regular pattern of the stellar wobble. For a Saturn-mass planet at a couple of astronomical units from a sun-like star, the resulting stellar velocity variation is on the order of tens of meters per second. Modern spectrographs can measure velocity changes of less than 1 meter per second on bright stars under ideal conditions. That should be sufficient to detect such a planet. But at Alpha Centauri, there's a complicating factor that dwarfs this planetary signal in size. The two stars are orbiting each other, and that binary orbital motion creates velocity variations of hundreds of meters per second or more in each star's spectral lines. Before you can look for a planetary signal, you have to subtract the binary orbit, and that subtraction is imperfect. Errors in the binary orbit model leave residuals in the data leftover variations that weren't properly accounted for. Those residuals can, and demonstrably do, look like planetary signals. This is exactly what happened in 2012, when a research team announced the detection of an Earth-mass planet orbiting Alpha Centauri B. The announcement dominated science news for weeks. Our nearest neighbor had a world. Then, the scientific community scrutinized the analysis. They found that the supposed planetary signal was almost certainly a residual of the binary subtraction, an artifact that the analysis method inadvertently introduced rather than removed. The result was subsequently questioned, then effectively withdrawn from consideration. That episode set the background for everything that followed. This is a system where the astronomical community has been burned before. The bar for a credible detection at Alpha Centauri is appropriately higher than almost anywhere else. Any new claim faces not just standard peer review, but the institutional memory of the 2012 false alarm. So when James Webb turned its instruments toward Alpha Centauri A, the context it was operating in was not just the general excitement of a powerful new telescope doing science. It was also the accumulated caution of a field that had learned from direct experience that Alpha Centauri will give you what looks like a planet if you're not careful enough. James Webb is an infrared telescope. That single fact is the core of why this story is different from every previous Alpha Centauri planet hunt. Most planet hunting instruments applied to this system over the past few decades work primarily in visible light, the part of the electromagnetic spectrum our eyes can see. Webb was built to observe in the mid-infrared. That means thermal radiation. It means heat. Everything with a temperature above absolute zero emits infrared radiation. The peak wavelength of that emission shifts with temperature. Very cold objects emit mostly in the far infrared, warm objects in the mid-infrared, very hot objects primarily in ultraviolet and visible light. Stars are so hot that they emit most of their energy at visible and ultraviolet wavelengths, but they also radiate in the infrared. Planets don't just reflect their star's light back into space. They absorb energy from their star and re-emit it as thermal infrared radiation at a temperature set by how much energy they receive and how effectively they can radiate it away. Gas giants. Planets comparable in mass to Jupiter or Saturn are large enough and retain enough internal heat from their formation that they glow distinctly in the mid-infrared. Young gas giants, still warm from the energy released during their rapid formation, glow more brightly. Even older, cooler gas giants emit thermal radiation in the mid-infrared. At these wavelengths, the contrast between a star and a planet improves substantially compared to visible light. In visible light, the ratio of a star's brightness to an orbiting planet's brightness is typically somewhere between 100 million to 1 and 10 billion to 1. That ratio is so extreme that seeing a planet next to its star in visible light is like trying to see a firefly hovering next to a searchlight from a mile away. In the mid-infrared, that contrast ratio compresses considerably for warm gas giant planets. It's still challenging, the star is still far brighter than the planet, but the gap is smaller. And smaller gaps mean the possibility of direct detection becomes real with the right instrument. Webb has a primary mirror, 6.5 meters in diameter, an assembly of 18 hexagonal, gold-coated beryllium segments that fold for launch and deploy to working configuration in space. Its total light-collecting area is roughly 6.5 times the light-collecting area of the Hubble Space Telescope. That larger mirror is critical. More collecting area means more photons gathered from faint sources in a given observation time. More photons means better signal-to-noise. Better signal-to-noise means fainter objects become detectable. Webb operates at the second Lagrange point, a gravitational equilibrium position about 1 million miles from Earth, on the side away from the Sun. This location was chosen with great care. From this position, Earth, the Moon, and the Sun are all in roughly the same direction. A large 5-layer sunshield, each layer thinner than a human hair, and stretched across an area roughly the size of a tennis court, blocks the thermal radiation from all three bodies. Without this shield, Webb's own temperature would be much higher, and its infrared-sensitive detectors would be blinded by its own thermal emission. With the shield, Webb's mirrors and instruments cool to temperatures as low as -233 degrees Celsius or -388 degrees Fahrenheit in the mid-infrared instrument. That cryogenic stability is what makes the mid-infrared observations possible. Webb also carries coronagraphs, instruments that mechanically block out the central glare from a target star, allowing fainter objects in the surrounding field to be detected. The mid-infrared instrument carries a coronagraphic mode specifically designed for this kind of planet hunting. It uses 4-quadrant phase masks, a sophisticated design that applies phase shifts to alternate quadrants of the stellar image, causing the star's light to interfere destructively and cancel. This produces better suppression of the star's light at small angular separations from the star than a simple circular blocking disk, which is precisely the regime needed for detecting planets around nearby stars. The team that pointed Webb at Alpha Centauri A was looking for thermal emission from planets, not a transit, not a radial velocity wobble. Actual infrared heat emanating from a planet's own atmosphere, spatially separated from the star's glare by the coronagraph, detectable directly. And in the initial data, something was there. To appreciate what a Saturn-mass detection would mean for the Alpha Centauri system, you need a clear picture of what Saturn itself represents as a world. Saturn is a gas giant. Its interior is primarily hydrogen and helium, the lightest elements in the universe, arranged in layers from gaseous at the top to compressed metallic hydrogen deeper down. It has approximately 95 times the mass of Earth. A planet that massive doesn't just sit quietly in a system, it dominates it gravitationally, shaping the orbits of everything else around it. A Saturn-mass world orbiting Alpha Centauri A would be a major discovery in any context. Alpha Centauri A is similar enough to our own Sun, slightly more massive, slightly more luminous, but broadly in the same stellar category that the parallels would be compelling and immediate. A Sun-like star with a confirmed gas giant companion would naturally raise questions about the system's full planetary architecture. And those questions would have direct implications for whether any part of that system could be relevant to discussions of planetary habitability. The detection wasn't a borderline statistical fluctuation sitting at the edge of significance. It was a coherent signal with properties consistent with what you'd expect from a point source of thermal infrared emission in the vicinity of Alpha Centauri A. The team ran their analysis carefully. They checked the signal against known instrumental behaviors. They examined its consistency across different data segments. They modeled Alpha Centauri B's contribution to the field around Alpha Centauri A and accounted for it in the analysis. And when they were satisfied enough with the result to put their names on it formally, they published. The paper's language was measured. Scientists writing for a skeptical community are always measured, but the conclusion was unambiguous. Strong evidence of a Saturn-mass giant planet orbiting Alpha Centauri A had been found in the Webb data. Then came the follow-up observations. Follow-up is not optional in modern exoplanet science. A single detection, no matter how internally consistent and carefully analyzed, is not enough to confirm a planet. The history of Alpha Centauri planet hunting makes this clear beyond any reasonable argument. You need the signal to persist across independent observations. You need to see it again, in the same place, with the same properties. A real planet orbits its star along a path governed by well-understood gravitational physics. Given a detection at one point in time and some constraint on the likely orbital parameters, you can calculate where the planet should be at any future epoch. A real planet shows up where the physics says it will be. So, the team went back. They pointed Webb at Alpha Centauri A, again, with exactly this test in mind. They ran the same analysis on the new data. They looked for the signal at the position where a gravitationally bound companion would be expected to appear. And the planet wasn't there. Not diminished. Not shifted to a slightly different position. Not ambiguous, sitting between detection and non-detection. Gone. This is a genuine problem, not a small discrepancy, not a marginal inconsistency. A real Saturn-mass gas giant orbiting a stable sun-like star does not disappear between observation epochs. The orbital dynamics of planetary systems are among the most precisely understood areas in all of physics. If a planet was present in the first dataset and is absent in the second, something has to explain the discrepancy. And the candidate explanations fall into several categories, none of which are comfortable. The first possibility is that the initial detection was a false positive. Not a planet, but something in the instrument, the data reduction pipeline, or the analysis methodology that produced a spurious signal convincing enough to pass the team's initial scrutiny. This is the most scientifically conservative interpretation, and the one being most actively investigated. Coronagraphic imaging in the mid-infrared is genuinely difficult, and the potential sources of systematic error are numerous and sometimes subtle. Infrared detectors have intrinsic noise properties that vary across the detector array. These variations are characterized during calibration, but calibration is never perfect. Residual detector non-uniformities can produce faint, structured signals in the science data if the calibration correction is slightly off. The coronagraph creates a characteristic pattern of diffracted light around the edges of the stellar mask. This pattern, called speckle noise, consists of a field of faint, light blobs scattered in the region around the block star. The speckles arise from tiny imperfections in the optical surfaces of the telescope and instrument, from the wave nature of light diffracting around the coronagraph mask's edges, and from any remaining wavefront errors in the telescope's mirror alignment. Speckles are not random noise. They have spatial structure. They appear as coherent blobs in the image, just like real astrophysical point sources. And they're not entirely stable. Speckles shift as the telescope's thermal state changes between observations. They vary with changes in the telescope's pointing and the precise alignment of the star on the coronagraph mask. An uncharacterized speckle, if it appears in the science image at a brightness consistent with what a planet would produce, can pass through an analysis pipeline and emerge as a candidate planet. The Alpha Centauri system adds a specific and substantial layer of difficulty here. Both stars are extremely bright. Alpha Centauri A is among the brightest stars in the southern sky. And because Alpha Centauri B is sitting nearby in the same field, B's light contributes to the field around A, even when A is the star being observed through the coronagraph. Separating B's contribution from A's requires careful modeling and subtraction. Errors in that subtraction leave structured residuals in the science image. If those residuals happen to be located at the angular position where a planet orbiting A could plausibly sit, they can appear as a planet candidate. This is not a theoretical concern. It's the specific type of systematic error that the Alpha Centauri team and the broader direct imaging community have been thinking carefully about. The investigation of whether this is what happened is ongoing and technically demanding. It requires detailed modeling of the instrument's optical behavior, precise characterization of how the two stars' light fields interact in the coronagraphic image, and careful comparison of the signal's spatial properties against what various types of artifacts would look like. None of this is quick work. None of it is easy. And the fact that it's being done carefully, and that the team is being transparent about the non-confirmation rather than quiet about it, reflects the kind of scientific integrity the field requires. The second possibility is that the initial detection was real, but the planet's infrared emission genuinely changed between the two observation epochs. Gas giants are not static objects. Their atmospheres are dynamic systems with storm patterns, cloud cover, and large-scale circulation regimes that can shift on timescales from days to years. In our own solar system, the giant planets demonstrate this variability clearly. Jupiter's Great Red Spot, a persistent anticyclonic storm, larger than Earth, influences the thermal structure of the atmosphere surrounding it. Jupiter's atmospheric banding structure varies in intensity over time. Its overall thermal emission in the mid-infrared shows variability at the level of a few percent correlated with its atmospheric activity. Saturn shows even more extreme variability during its periodic Great White Storm outbursts. Enormous convective events that erupt roughly every 30 years and dramatically alter the planet's atmospheric temperature structure for months before the atmosphere returns to its baseline state. A gas giant orbiting Alpha Centauri A would have its own atmospheric dynamics, shaped by its orbital distance, its mass, its internal heat flux, and the radiation it receives from its host star. If the planet was caught in an unusually active atmospheric state during the first observation, perhaps during a large-scale storm or enhanced convective event, its thermal emission could have been elevated above its typical level, making it detectable when it might otherwise not be. And if the atmosphere settled to a quieter state by the time of the follow-up observation, the emission could have dropped back below the detection threshold. This explanation has real physical problems as a complete account of the disappearance. A Saturn-mass gas giant doesn't dim itself by an order of magnitude on a timescale of months due to atmospheric variability. Atmospheric variability in giant planets is typically at the level of a few percent to perhaps 10 or 20% of the baseline emission. Disappearing entirely from a follow-up observation requires either that the first detection was barely above the noise floor and the atmospheric variation was enough to push it below that floor, or that the atmospheric variability was far more extreme than anything observed in our solar system's giant planets. Neither scenario is impossible, but both require specific conditions that haven't been independently established. The third possibility is that the detected object wasn't a planet orbiting Alpha Centauri A at all, but a background source, most likely a distant galaxy, that happened to fall near Alpha Centauri A's position during the first observation and was not at that position during the past. Follow-up. The universe is full of infrared bright galaxies. Some are undergoing intense bursts of star formation, producing vast numbers of massive, hot, young stars that heat the surrounding dust to temperatures that cause it to glow brightly in the mid-infrared. Others harbor active galactic nuclei, supermassive black holes, consuming gas and dust at rates that produce enormous amounts of energy across the electromagnetic spectrum, including the infrared. Many of these galaxies, being very far away, are compact enough to appear as unresolved point sources in telescope images, looking in an image just like a star or a planet. A background galaxy in the same field as Alpha Centauri A would not stay at the same apparent position relative to the star between two observations. Here's why. Alpha Centauri is an extremely nearby star. Nearby stars appear to shift their positions on the sky as Earth moves in its orbit around the Sun, a phenomenon called parallax. Nearby stars also physically move through space, producing an apparent drift across the sky called proper motion. Alpha Centauri has a large proper motion. It moves noticeably across the sky, even on human timescales, because it's so close to us that its actual space velocity translates into a large, apparent, angular motion. A background galaxy, being millions or billions of light-years away, has essentially zero parallax and unmeasurably small proper motion. So as Alpha Centauri A moves across the sky between two observation epochs, any background objects near it appear to shift relative to the star. Objects that were at a certain angular separation from Alpha Centauri A in one observation will appear at a different angular separation in a subsequent observation, taken weeks or months later. A real planet, bound gravitationally to Alpha Centauri A, would move with the star. Its position relative to Alpha Centauri A would remain constant between epochs, possibly with a small orbital motion. A background galaxy would appear to move in the opposite direction to Alpha Centauri's proper motion, staying at a fixed sky position while the star moves away from it. Checking whether the detected object's position in the second observation is consistent with a planet or with a background source is one of the first tests applied to any imaging candidate. The team has been performing this analysis. The results of the complete background contamination check have not yet been published, but this test will be one of the primary discriminants in the team's final assessment. To understand what could reasonably orbit Alpha Centauri A, you have to understand what the presence of Alpha Centauri B does to the planet formation environment. The protoplanetary disk around Alpha Centauri A was not forming in isolation. It was forming in the gravitational shadow of a companion star. When a star system forms, it begins as a rotating cloud of molecular gas and interstellar dust collapsing under its own gravity. Conservation of angular momentum causes this collapse to flatten into a rotating disk material in the cloud that has too much angular momentum to fall directly onto the forming star, instead settles into a plane and orbits it. This protoplanetary disk is where planets form. Dust particles collide, stick together, and gradually accumulate into larger and larger bodies over timescales of millions of years. For a system with a binary companion like Alpha Centauri's configuration, the companion star's gravity imposes tidal forces on the disk of the primary. These tidal forces truncate the disk. They disrupt and eject material at the outer edges of the disk that would otherwise remain in orbit and eventually contribute to planet formation. The truncation radius, the distance from the primary beyond which the disk is disrupted, depends on the binary's mass ratio, their orbital separation, and the eccentricity of their orbit. For Alpha Centauri A's configuration, models suggest truncation at roughly 2 to 3 astronomical units. Our own solar system's protoplanetary disk extended out to 50 or more astronomical units. The disk around Alpha Centauri A was dramatically more compact. This has direct consequences for what kinds of planets could form there. In our solar system, the giant planets formed in the cold outer disk, beyond the ice line, the distance from the Sun at which water ice could condense. Water-ice condensation dramatically increased the mass of solid material available in the disk, allowing planetary cores to grow massive enough to gravitationally capture large envelopes of hydrogen and helium. Jupiter formed at roughly 5.2 astronomical units from our Sun. Saturn formed at about 9.5 astronomical units. If Alpha Centauri A's disk was truncated at about 2 to 3 astronomical units, the formation environment for gas giants was compressed into a much smaller physical space. The ice line, for a star slightly more luminous than our Sun, would sit at roughly 2 astronomical units right near the disk's outer truncation boundary. A gas giant forming around Alpha Centauri A would have been doing so in a much more restricted volume of disk material than Saturn had available in our solar system. This doesn't make it impossible. Some planet formation models suggest that the compression of material in a tidally truncated disk can actually accelerate certain formation processes. Others suggest that the companion's perturbations inhibit the assembly of planetary cores in specific orbital regions. The honest answer is that we have limited direct data on how planet formation proceeds in binary systems of this specific configuration, and the theoretical predictions are not all in agreement. What makes the Webb detection physically interesting is that a Saturn-mass planet at Alpha Centauri A is not implausible in the framework of any leading planet formation model. It's not the expected canonical outcome, but it's also not an outlier that the models refuse to accommodate. It's a possible outcome, which is part of why the detection was published rather than immediately dismissed. Understanding the architecture of Alpha Centauri A's potential planetary system matters beyond just the immediate detection question. If there's a Saturn-mass giant in that system, it has been gravitationally shaping everything else, orbiting Alpha Centauri A for billions of years. Gas giants in planetary systems are not passive occupants. They're the dominant gravitational architects. In our own solar system, Jupiter's gravity has scattered comets and asteroids throughout the inner system, deflecting impactors that might otherwise have struck Earth more frequently. Jupiter's gravitational resonances with the asteroid belt have carved gaps into the belt's structure, the Kirkwood gaps, and helped maintain the distribution of material in the belt over billions of years. Jupiter and Saturn's combined gravitational influence created the Late Heavy Bombardment, a period roughly 3.9 billion years ago when the inner solar system experienced a dramatic increase in impactor flux, possibly triggered by a shift in the giant planet's orbital resonances. That bombardment delivered enormous quantities of water and organic molecules to Earth, and may have been a crucial event in the early history of life on our planet. A gas giant orbiting Alpha Centauri A has been performing analogous functions in that system for its entire history. It has been deflecting comets and asteroids, delivering or withholding volatile materials from inner orbits, and shaping the orbital architecture that any inner rocky planets would have formed within. Whether those inner rocky planets actually exist is not something the current Webb data can tell us. The mid-infrared coronagraphic technique is most sensitive to large, warm planets. Smaller, rocky worlds at closer orbital distances, which would be much fainter in the infrared, are beyond the current detection capability. But the existence of a gas giant is a meaningful prior for thinking about what else might be in the system. Systems with gas giants tend to be complex, multi-component planetary systems. Our own is one example. The TRAPPIST-1 system has no gas giants and is dominated by closely packed rocky worlds. Alpha Centauri A, with a confirmed Saturn-mass planet, would look more like our own solar system in its broad architecture than like TRAPPIST-1. And that comparison has implications for what kinds of smaller worlds might accompany the giant. The James Webb Space Telescope's coronagraphic capabilities represent a watershed moment in what's technically achievable at nearby star systems. But precision about what those capabilities are and where they fall short is essential for understanding the Alpha Centauri situation. Webb's coronagraphic imaging works best for planets at relatively large angular separations from their host stars. Angular separation is the apparent distance between the planet and the star as seen from Earth, measured in arc-seconds. The inner working angle of a coronagraph is the minimum angular separation at which the instrument can detect a companion, the boundary inside which the coronagraph's own diffraction structures dominate and real sources become undetectable. For MIRI's 4-quadrant phase mass coronagraph, the inner working angle is roughly 0.3 to 0.4 arc-seconds, depending on wavelength. At Alpha Centauri A's distance of 4.37 light-years, 1 astronomical unit corresponds to about 0.74 arc-seconds on the sky. So the inner working angle corresponds to a physical separation of about 0.4 to 0.5 astronomical units from Alpha Centauri A. Any planet orbiting closer than roughly half an astronomical unit from Alpha Centauri A would be inside the coronagraph's inner working angle and completely undetectable with this technique. The habitable zone of Alpha Centauri A, the region where surface temperatures could allow liquid water on a rocky planet, sits at roughly 1.2 astronomical units from the star. At that distance, the angular separation from Alpha Centauri A is about 0.9 arc-seconds. That's just outside the inner working angle. In principle, a planet in Alpha Centauri A's habitable zone could be detectable with Webb's coronagraph. In practice, detecting a rocky planet in the habitable zone of a nearby star is far beyond current capabilities. Even with Webb, the planet would be too small and too faint. What Webb can potentially detect is a large gas giant at a moderate orbital distance, something like a Saturn-mass planet at 2 or 3 astronomical units from the star. At those distances, the angular separation from the star is roughly 1.5 to 2.2 arc-seconds, well above the inner working angle. And at those distances, a gas giant with a moderate atmospheric temperature would have thermal emission in MIRI's wavelength range that, in principle, rises above the noise floor. The phrase, "in principle," is doing real work here. The noise floor at Alpha Centauri A, the level below which real signals become indistinguishable from instrumental artifacts, is set by the combination of the coronagraph's speckle, suppression, the stability of Webb's pointing and thermal state during the observation, and the accuracy of the binary star subtraction. These factors combine to produce a specific contrast ratio that determines what kind of planet, at what orbital distance, is detectable. The team that performed the initial observation characterized this noise floor carefully. The detected signal appeared above that floor by a margin that was significant enough to report. The question the ongoing investigation is trying to answer is whether the noise floor characterization itself was accurate, or whether there were unmodeled systematic effects that caused the actual noise floor to be higher than estimated. If the true noise floor was higher than estimated, if the systematic errors were larger than the team accounted for, then the signal might have been within the noise all along, and the detection would be a false positive. If the noise floor characterization was accurate, then a real astrophysical source produced the signal, and it needs to be accounted for. That distinction is what the ongoing analysis is working to establish. The planned follow-up observations have been designed to address this ambiguity as directly as possible. The most important addition to the observing strategy is systematic roll-angle diversity, what astronomers call angular differential imaging. When Webb rotates around its pointing axis while keeping it aimed at the same target, all instrumental artifacts in the coronagraphic image rotate with the telescope. Real astrophysical sources stay fixed on the sky. By observing at two or more distinctly different roll angles, you can combine the images in a way that makes artifacts cancel and real sources survive. If you subtract two images taken at different roll angles, a speckle that was at position X in the first image has moved to position Y in the second. The subtraction leaves a negative blob at Y and a positive blob at X, revealing the speckle as an artifact. A real planet at position Z appears as a positive-negative pair, straddling Z as the rotation angle changes, which is the signature of a real source rather than a rotating artifact. This technique is widely used in ground-based direct imaging programs and has been applied to some degree in the initial observations. The new observations use a more optimized roll angle separation and a tighter temporal schedule to minimize speckle evolution between rolls. The second major refinement involves the reference star observations used to model and subtract the residual stellar diffraction pattern. In coronagraphic imaging, you typically observe a reference star, a star similar to your target in brightness and color, and use its diffraction pattern as a template to subtract from the science image. The quality of this subtraction depends critically on how well the telescope's thermal and optical state is matched between the target and reference observations. Even small changes in the telescope's temperature between observations can cause the speckle pattern to evolve, reducing the accuracy of the reference subtraction. The new observation program uses a more carefully chosen reference star and a more tightly constrained observation sequence to maximize the similarity of conditions between target and reference. Combined with longer total integration, times more observing, hours spent staring at Alpha Centauri A, these refinements are designed to push the effective noise floor down to the point where the distinction between a real planet and a false positive becomes unambiguous. While the Webb analysis is ongoing, complementary data streams from other instruments are contributing to the picture. The Atacama Large Millimeter Array, is a configuration of 66 high-precision millimeter-wavelength radio antennas spread across the Atacama Desert in Chile. It's sensitive to thermal emission from cool dust, the debris disk material that persists around stars long after the planet formation era has ended. Debris disks are maintained by ongoing collisions between larger, rocky or icy bodies, asteroids, and comets that continuously grind themselves into smaller and smaller fragments, producing fresh dust that the disk maintains against the forces of radiation pressure and stellar wind that would otherwise sweep it away. The structure of a debris disk is not random. It's shaped by the gravitational presence of planets. A planet orbiting within a debris disk creates a gap. It sweeps its orbital zone clear and, in some cases, drives material into resonant clumps that pile up at specific orbital distances relative to the planet. A planet just interior to a debris disk creates a sharp inner edge where the disk appears to be truncated by the planet's gravitational clearing. ALMA observations of the Alpha Centauri system have been used to search for the thermal emission of cold disk material. These observations place constraints on the amount of dust present at various distances from each star, and can potentially reveal structural features in the disk that would be consistent or inconsistent with the presence of the Webb candidate planet. If the disk shows a gap or truncation at the orbital distance inferred for the planet candidate, that would be circumstantial supporting evidence. If the disk shows no such structure, that's informative too. Though the interpretation is complicated by the disk's overall faintness and the difficulty of spatially resolving fine structure at Alpha Centauri's distance. There are also ongoing precision radial velocity programs monitoring Alpha Centauri A. If the planet candidate is real and has the orbital properties implied by the Webb detection, it would produce a stellar reflex velocity of tens of meters per second in Alpha Centauri A's spectrum. Modern spectrographs like Espresso at the Very Large Telescope are capable of measuring velocities at this level on suitable targets. The challenge at Alpha Centauri remains the binary subtraction, removing the large binary orbital signal accurately enough to reveal the much smaller planetary signal. But with extended baseline monitoring and improved analysis techniques developed since the 2012 episode, the radial velocity approach is substantially more capable now than it was then. A consistent periodicity in the radial velocity residuals of Alpha Centauri A, at a period and amplitude matching the orbit implied by the Webb candidate's position, would be powerful supporting evidence. The integration of radial velocity data with Webb imaging data is one of the most compelling paths to a robust confirmation. But the single most anticipated event in the near-term investigation of this system isn't a radial velocity measurement or a disk structure map. It's a date on the calendar. The orbital simulations that Sanghi and Beichmann ran after the disappearance didn't just explain why the planet went missing in February and April of 2025. They also predicted when it should come back. If the 2019 ground-based detection and the 2024 Webb detection both captured the same object, and the orbital models suggest that's the most coherent interpretation of all four data points combined, then the planet's elliptical path would carry it back into a detectable position in August 2026. Same time of year as the original detection. Same orbital geometry. The team has said publicly they intend to apply for telescope time to make exactly that observation. If it's granted, August 2026 becomes the most consequential single observation in the history of Alpha Centauri planet hunting. Either the planet reappears, where the models predict, and the case for a real world at our nearest neighbor becomes very difficult to dismiss, or it doesn't, and the investigation moves into a different phase entirely. That's what orbital mechanics looks like when it's working in your favor. The planet, if it's real, doesn't get to hide forever. Its orbit is a clock, and the clock is already running. And there's a second instrument entering the picture around the same time. NASA's Nancy Grace Roman Space Telescope is scheduled to launch by May 2027, with a possible earlier launch window as soon as late 2026. Roman is considerably smaller than Webb. Its mirror is 2.4 meters across compared to Webb's 6.5, but it carries a coronagraph that was custom-built, specifically for imaging planets around nearby stars. That's not a secondary capability bolted onto a broader mission. It's the design goal. Roman observes invisible light rather than the mid-infrared, which means it measures reflected starlight from a planet's atmosphere rather than the planet's own thermal glow. Where Webb tells you about a planet's temperature and heat emission, Roman tells you about its size, its reflectivity, and what its upper atmosphere is doing. The two telescopes measure fundamentally different things, and together they build a picture neither can produce alone. If Webb sees the planet again in August 2026, Roman becomes the instrument that characterizes what Webb found. If Webb doesn't see it, Roman provides an independent search from a completely different observational angle. Either way, the next 2 years are not a period of waiting. They're a period of narrowing each observation, tightening the constraints, each detection or non-detection reshaping the probability until the answer finally comes into focus. Proxima Centauri, the third member of the system, provides useful context for understanding what we're looking for and why. Proxima is the nearest star to Earth at 4.24 light-years. It's a red dwarf, small, cool, magnetically active, and far less luminous than our Sun. It has roughly 12% of the Sun's mass and about 14% of its diameter. It's so faint that despite being our nearest stellar neighbor, you cannot see it without a telescope. Proxima has at least 2 confirmed planets. Proxima b was confirmed in 2016 using the radial velocity method. It has a minimum mass of roughly 1.07 Earth masses, placing it in the rocky planet size range. It orbits in the star's habitable zone, the range of distances at which liquid water could potentially exist on a rocky surface. The orbital period is 11.2 days. Proxima d was confirmed in 2022, smaller still, orbiting even closer to the star with a period of just 5 days. The problem is the star itself. Proxima is a magnetically hyperactive red dwarf that produces violent stellar flares on a regular basis. During major flare events, Proxima's X-ray and extreme ultraviolet output can increase by a factor of hundreds compared to its quiescent state. For a planet orbiting as close as Proxima b does, closer than Mercury orbits our Sun, this radiation environment is intense and relentless. Models of atmospheric erosion under this type of bombardment suggest that a planet in Proxima b's position would lose its atmosphere on geological timescales unless it has an extraordinarily strong magnetic field, protecting it from the stellar wind and radiation. Whether Proxima b retains enough atmosphere to be relevant to habitability discussions is genuinely unknown. We don't currently have instruments capable of detecting and characterizing an atmosphere on a planet at that distance. Alpha Centauri A presents a completely different scenario. It's a stable, middle-aged, sun-like star with activity levels similar to or slightly below our own Sun. its flare rate is low. Its X-ray and ultraviolet output is calm. A planet in the habitable zone of Alpha Centauri A would receive a radiation environment similar to Earth's, challenging, but not the relentless bombardment that Proxima's planets endure. This is one of the most important reasons the planet-hunting focus on Alpha Centauri A is scientifically meaningful beyond just confirming or denying a specific candidate. The star itself is the kind of star where planets in stable orbits could maintain conditions relevant to complex chemistry and potentially to life over geological timescales. The gas giant candidate, detected by Webb, is obviously not itself in the habitable zone. Gas giants don't have surfaces on which life, as we understand it, could exist. But a confirmed gas giant implies a complex planetary system, and a complex planetary system around a stable, sun-like star at 4.37 light-years is the kind of finding that reshapes the scientific and philosophical context of our local stellar neighborhood. The broader project of human engagement with the Alpha Centauri system has been gaining momentum beyond the purely scientific domain in ways that make the Webb result practically relevant, as well as scientifically important. Breakthrough Starshot is the most prominent example. Announced in 2016 with the involvement of Stephen Hawking, Yuri Milner, and a team of distinguished physicists and engineers, Breakthrough Starshot is a long-term project to develop the technology needed to send physical probes to the Alpha Centauri system. The concept is this: a ground-based laser array of enormous power focuses its combined beam on a gram-scale spacecraft, essentially a chip carrying cameras, sensors, and communication hardware, mounted on a large, thin light sail. The laser pressure accelerates this spacecraft to roughly 20% the speed of light. At that velocity, the crossing to Alpha Centauri takes approximately 20 to 25 years. The probes would fly through the Alpha Centauri system at high speed, with minutes to hours of observation time near closest approach. During that window, they would photograph any planets, measure whatever spectra they could, and transmit the data back to Earth over the following 4+ years. The physics of this concept is not science fiction. Laser propulsion is real. Photon pressure is real. The principle of using concentrated laser light to push a lightweight sail to high velocities is fully consistent with known physics. The Planetary Society successfully demonstrated a solar sail in space with the light sail missions. The fundamental concept is established. The engineering to build the full Breakthrough Starshot system is an entirely different matter. The laser array needed would have to deliver power levels far beyond anything currently built, focused with precision that exceeds current adaptive optics capabilities, sustained for the duration of the acceleration phase. Atmospheric turbulence distorts laser beams as they pass upward through the air. Compensating for that distortion at the required intensity and scale requires adaptive optics systems of a sophistication not yet achieved. The spacecraft itself would face the hazard of interstellar dust impacts at 20% the speed of light. At that velocity, even a hydrogen atom represents a collision with significant energy. A submicron dust grain, encountered at this speed, carries the energy of a high-velocity rifle bullet in terms of its impact on a gram-scale spacecraft. Over 20 years of flight through the interstellar medium, cumulative damage from these impacts could be substantial. None of these challenges are physically forbidden from being solved. but none of them are close to solved with current technology. The project's scientific leadership has been honest about this. The goal is to begin the necessary research and development now, so that the engineering might become feasible within a few generations. What Breakthrough Starshot represents for our current discussion is this. The Alpha Centauri system is close enough that humanity has developed a serious, scientifically grounded, engineering-supported proposal to actually send physical probes there. Not in the distant, hypothetical future. As a specific project, with a specific design and a specific research agenda aimed at making it real. Whether there are planets in that system, and what kinds of planets they are, directly shapes what any Breakthrough Starshot probe would be flying toward. A confirmed Saturn-mass giant, and the implied complexity of a system with such a planet changes the scientific return profile of a probe mission. It changes what instruments you'd want to put on the spacecraft. It changes what observations you'd prioritize during the brief flyby window. The Webb result, therefore, isn't just an academic scientific question. It's directly informing the strategic thinking around one of the most ambitious, long-range engineering proposals humanity has ever produced. The history of Alpha Centauri as a planet-hunting target spans several decades and has the character of a story that keeps arriving at false summits. Each time the community has developed a new technique capable of searching the system, it has produced results that were initially promising and ultimately inconclusive. The radial velocity searches of the late 1990s and 2000s accumulated thousands of observations, built detailed models of the binary orbit, and found no compelling planetary signal. The imaging searches of that era were similarly unproductive, constrained by the limitations of ground-based coronagraphs operating through Earth's turbulent atmosphere. The 2012 announcement introduced the idea of a planet, made it real in public imagination, and then was walked back as the analysis was scrutinized. The transit searches that followed using small, purpose-built telescopes dedicated entirely to monitoring Alpha Centauri's photometric variability found no convincing transit signals. Each campaign advanced the field's understanding of the system and tightened constraints on what could be there. But none produced a confirmed planet. Into this context, James Webb arrives with a fundamentally different approach. Direct infrared imaging from space, using a coronagraph of unprecedented capability, observing at wavelengths where the planet-to-star contrast is most favorable for warm gas giants. The initial detection, whatever its ultimate explanation represents, the first time the community has a result from Webb at this target that was compelling enough to publish. That is, in itself, a milestone. Whether the planet is confirmed, found to be a false positive, or determined to be a background source, the process of investigating this result with Webb will fundamentally improve our understanding of what's orbiting Alpha Centauri A. The constraints from the analysis will be the tightest ever placed on the system's planet population, and the refinements to coronagraphic technique that emerge from this campaign will benefit planet hunting at Alpha Centauri and at every other nearby star system that future programs attempt to characterize. What we know right now is this. James Webb looked at Alpha Centauri A with its mid-infrared coronagraph. The initial data contained a signal, coherent, spatially resolved, consistent in its properties with the thermal emission of a Saturn-mass planet. Follow-up observations did not reproduce that signal in the expected location. The team is investigating three primary explanations. The first is an instrumental artifact, something from the complex optical environment created by imaging a bright binary system so close to the inner working angle of the coronagraph. The second is a background infrared source that appeared near Alpha Centauri A in the first observation and shifted to a different relative position in the second because of Alpha Centauri's proper motion across the sky. And the third is a real planet, one whose detection was marginal and whose signal was affected by atmospheric variability, orbital geometry, or the evolving speckle pattern between the two epochs. Additional Webb observations have been scheduled, incorporating angular differential imaging at optimized roll angles, more carefully matched reference star observations to improve speckle subtraction, and extended integration times to push the noise floor down. Parallel programs with ALMA are analyzing circumstellar disk structure for features consistent or inconsistent with the planet candidate. Radial velocity programs at precision spectrographs are searching Alpha Centauri A's spectrum for the stellar wobble a Saturn-mass companion would produce. Independent teams are analyzing the original data. The result is not confirmed. The result is not retracted. It exists in the state that responsible science occupies when confronted with a genuinely ambiguous result at the frontier of what's technically achievable. That intermediate state is uncomfortable in a media environment that prefers clean outcomes. But it's the accurate description of where things stand, and it's worth sitting with for a moment. Science at the frontier is almost never clean. The history of astronomy is full of results that seemed definitive and turned out to be artifacts. It's also full of results that were initially questioned, withstood scrutiny, and became foundational knowledge. The difference between those two outcomes is almost always the quality and quantity of follow-up investigation. The Alpha Centauri community has done this correctly. The initial detection was published because the team was confident in their initial analysis. The follow-up was immediate because the community knows what's at stake and what the history demands. The non-confirmation was acknowledged publicly because transparency is the only responsible response to a discrepancy. And the ongoing investigation is thorough because a result this significant deserves every available tool brought to bear on it. Whatever the answer ultimately is, it will be the most rigorously established assessment of Alpha Centauri A's planetary population that science has ever produced. That matters. Even a definitive non-detection, even concluding with high confidence that there is no Saturn-mass planet at the position, and orbital distance implied by the initial signal is enormously valuable. It tells mission planners something concrete about the system. It constrains the system's architecture in a way that shapes scientific and engineering decisions going forward. It defines the limits of Webb's current capability at this target and points to what improvements in technique or instrumentation would be needed for a deeper search. Negative knowledge is real knowledge. And, in the case of the nearest star system, any genuine knowledge is precious. There's a specific question that cuts to the heart of what makes this Webb result so interesting, and it's worth spending real time on it. Why would a planet that appeared convincingly in one set of observations not appear in a follow-up taken weeks or months later? The instinctive reaction is to say that the first detection must have been a mistake, and that might be right. But the instinctive reaction isn't always the correct one, and dismissing the result too quickly would itself be an error. To understand the range of possibilities properly, you need to understand something about how direct imaging of exoplanets actually works in practice, not as an idealized theoretical procedure, but as it plays out at the telescope, in the analysis pipeline, and in the messy reality of trying to detect a planet that is many orders of magnitude fainter than the star it orbits. The process of coronagraphic direct imaging is best understood as a long chain of subtractions. You start with a raw image from the detector. That image contains light from several distinct sources. There's the star itself, but even though the coronagraph blocks most of the star's direct light, some leaks through. There's the stellar diffraction pattern, the system of speckles and rings created by diffraction of the star's light around the edges of the coronagraph mask. There's background from the thermal emission of the telescope structure itself, which is small but not zero, even at Webb's operating temperature. There's detector noise, the intrinsic electronic noise of the infrared detectors, which creates a faint, spatially varying background in every image. And then, buried somewhere underneath all of those contributions, there might be a planet. To find the planet, you have to subtract away everything else. You subtract the thermal background. You subtract the detector noise pattern. You subtract the stellar diffraction pattern using observations of a reference star. You apply the angular differential imaging technique, combining observations at different roll angles to suppress the rotating speckle pattern. Each subtraction step removes some of the unwanted signal. But each subtraction also introduces its own uncertainty. If the reference star's diffraction pattern doesn't perfectly match the target star's diffraction pattern because the telescope's thermal state was slightly different, or because the reference and target have slightly different brightnesses or colors, or because pointing was slightly imperfect, the subtraction leaves a residual. Those residuals are spatially structured. They appear as blobs, or rings, or asymmetric features in the final image. And if one of those residuals happens to have a compact, point-like morphology and sits at an angular separation from the star that a planet could plausibly occupy, it shows up in the analysis as a candidate. The team performing the analysis applies multiple tests to each candidate. They look at the candidate's spectral energy distribution, its brightness at different wavelengths, to see if it's consistent with a planet rather than an artifact. Planets and speckles have different spectral behaviors, and a candidate that passes all the spectral consistency tests is more credible. They check whether the candidate appears consistently across different sub-segments of the data. If it's real, it should be present in early exposures and late exposures alike. They examine the candidate's spatial profile. A real planet should look like a point source convolved with the telescope's point spread function, while some artifacts have different spatial structures. They run simulations of what various types of artifacts would look like in the data and compare those simulated artifacts to the actual candidate. The detected signal at Alpha Centauri A passed enough of these tests to be reported. Not all of them. If it had passed all tests definitively, the non-detection in follow-up would be even more puzzling. But enough that the team was confident enough in the result to publish it as strong evidence rather than a tentative hint. The follow-up observation is the test that no analysis of a single epoch dataset can substitute for. It's the one test where a real planet and an artifact diverge unambiguously. Real planets persist. Artifacts don't. Or at least, they don't persist at the same position in the same way. The fact that the follow-up did not confirm the signal doesn't automatically mean the initial detection was wrong. It means the signal has to be explained. And explaining it carefully, systematically, and honestly is exactly what the team is doing. One aspect of this story that doesn't get enough attention is the difficulty of choosing exactly where to look. A planet orbiting Alpha Centauri A is not sitting still while you observe. It's orbiting. And its orbital period, the time it takes to complete one full orbit, depends on how far it is from the star. At 1 astronomical unit from Alpha Centauri A, the orbital period would be about 1 year, similar to Earth's orbital period. At 2 astronomical units, about 2.8 years. At 3 astronomical units, about 5 years. For a planet at 2 astronomical units, the planet moves through roughly 130 degrees of its orbit in a single year. That's significant. If you detect the planet at one position and then wait 6 months to observe again, the planet has moved through about 65 degrees of its orbit. Its position relative to Alpha Centauri A in the image has changed substantially. To detect the planet in the second observation, you need to know where it's going to be. And to know where it's going to be, you need to know its orbital period, which requires knowing how far it is from the star. If the initial detection gives you an approximate position, you can calculate a range of possible orbits that are consistent with that position. Different assumptions about the orbit's circular versus eccentric, different inclinations relative to the plane of the sky produce different predictions for where the planet will appear in subsequent observations. If the follow-up is pointed at the right position for the most likely orbit, and the planet is in fact on a different orbit, the follow-up might simply miss the planet, not because the planet isn't there, but because it's at a different position than predicted. This possibility is part of the reason that the follow-up observation design for ongoing programs includes broad coverage around the predicted position, not just a single pointed measurement at the single most likely location, but coverage of the range of positions consistent with the uncertainties in the initial detection. Understanding whether the follow-up covered the right range of positions is part of the ongoing analysis. If the planet was genuinely in the field of view, but the analysis missed it because the data reduction didn't extend to the right position, or because the noise at that position was higher than elsewhere, that's different from the planet genuinely not being there. These distinctions matter, and they require careful analysis of the follow-up data with explicit attention to what positions were and weren't effectively covered. Alpha Centauri's historical role as a target for imagined interstellar travel is worth considering in the context of this scientific search, because it illuminates something about the human relationship to this system that goes beyond pure astronomy. For as long as humanity has known that stars are suns, and that our sun is a star, the nearest star has held a special place in the imagination. Alpha Centauri was identified as the nearest stellar neighbor with increasing precision through the 19th and early 20th centuries, as parallax measurements of stellar distances improved. By the mid-20th century, Alpha Centauri's status as the closest star system was firmly established, and its proximity made it the natural destination in countless science fiction narratives about interstellar travel. Robert Heinlein set stories there. Ursula Le Guin placed worlds around nearby stars that captured the imagination of readers for generations. The planetary system around Alpha Centauri served as the backdrop for the film Avatar, A World Called Pandora, orbiting a fictional gas giant called Polyphemus in the Alpha Centauri system. These cultural representations matter because they shaped public expectations about what we might find there. In the science fiction imagination, Alpha Centauri has planets. It has interesting planets. It has planets that matter. The scientific reality has, until now, refused to cooperate with that expectation. Every search has come up empty or uncertain. The Webb result, whatever it ultimately means, is the first time the scientific evidence has produced something, a signal, a candidate, a real puzzle, rather than just constraints and limits. Even if the candidate turns out to be a false alarm, The fact that Webb was capable of producing a signal strong enough to publish marks a qualitative shift from the decades of null results that preceded it. The gap between scientific capability and the kind of knowledge the public imagined we would have about our nearest neighbor is finally beginning to close. Not because we found what science fiction imagined, but because we finally have instruments that could find it if it's there. The physics of what happens when a gas giant forms in a binary star system, as opposed to around a single star, has been studied extensively with computer simulations in recent years. These simulations model the evolution of a protoplanetary disk under the combined gravitational influence of the primary star and the binary companion. What they consistently show is that binary companions don't simply make planet formation impossible. They change its character. The companion's gravity truncates the outer disk, as described earlier. But inside that truncation radius, planet formation can proceed. The key difference is the orbital eccentricities that the companion's perturbations excite in the disk material. In a protoplanetary disk around a single star, the orbital eccentricities of the dust and gas are typically very small. The disk is nearly circular. Particles collide with relatively low relative velocities, making it easier for them to stick together rather than fragment. In a tidally perturbed disk around one member of a binary, the companion's gravity excites eccentricities. Particles don't all move on circular orbits. They're on eccentric orbits with different orientations. When they collide, the relative velocities are higher. Higher collision velocities mean more energetic impacts. And more energetic impacts mean that instead of particles sticking together and growing, they fragment, eroding away from each other. This fragmentation barrier is a real challenge for planet formation in binary systems. It can slow or prevent the growth of planetesimals in certain orbital regions. But it doesn't completely shut down planet formation. The inner regions of the disk, where the companion's perturbations are weaker due to the greater physical distance from the companion, tend to be less affected. Rocky planetary embryos can form in those relatively sheltered regions. And once planetary embryos reach a certain size, roughly the mass of the Moon, or larger, they're massive enough to gravitationally dominate their local environment, sweeping up material despite the elevated collision velocities. So the picture that emerges from simulations is this. Rocky planet formation around Alpha Centauri A, in the inner 1 or 2 astronomical units from the star, is plausible despite the binary companion. Giant planet formation, which requires the accumulation of a massive solid core before gas can be captured, is more challenging because the core needs to form quickly in the outer disk before the gas dissipates, and the binary companion's perturbations can slow this process. Some simulations suggest that giant planet formation around Alpha Centauri A is significantly inhibited compared to single stars. Others find that it's possible if the initial disk mass is high enough, and if the formation timescale is within the window when gas is still present. The Webb candidate, if confirmed, would be observational evidence directly constraining these theoretical models. A real Saturn-mass planet at Alpha Centauri A would tell us that giant planet formation in this binary configuration is indeed possible, and would push theorists to understand how it happened. A confirmed absence of giant planets, established rigorously through deep observation, would equally constrain the models by showing that the binary companion's perturbations are effective enough to prevent giant planet formation at the scales currently accessible. Either result is a win for the theory. The data is what science needs, regardless of which direction it falls. The broader context of what Webb has revealed about exoplanets in its first few years of operation is worth reviewing, because it establishes what the telescope is actually capable of and why the Alpha Centauri attempt is scientifically credible, even in the face of the initial non-confirmation. Webb's first year of science operations produced results that exceeded expectations in several areas. The telescope's ability to characterize exoplanet atmospheres through transmission spectroscopy, observing the way a planet's atmosphere filters starlight during a transit, advanced dramatically. Webb detected carbon dioxide in the atmosphere of the hot Jupiter WASP 39b in some of the first science observations released. It detected sulfur dioxide, a potential biosignature in the right context in the same planet's atmosphere. It characterized the thermal emission spectrum of the super-Earth TRAPPIST-1b, finding no evidence of a substantial atmosphere, which was itself an important result for understanding the atmospheres of small rocky worlds orbiting red dwarf stars. Webb directly imaged the planet HIP 65426b, a young, massive gas giant orbiting a star about 385 light-years away, and characterized it across multiple infrared wavelengths in detail. It was the first exoplanet ever directly imaged by Webb, and the first ever detected at wavelengths beyond 5 microns. This was the first time such detailed atmospheric characterization had been achieved for a directly imaged planet. Webb observed the TRAPPIST-1 system in detail, searching for evidence of atmospheres on the system's rocky planets. The results have been mixed. Some planets show evidence of very thin or absent atmospheres, while others remain ambiguous. But the observational capability to address these questions at all represents a qualitative advance over what was possible with Hubble. Webb has detected polycyclic aromatic hydrocarbons in the atmospheres of distant exoplanets. It has measured wind speeds in the atmospheres of hot Jupiters. It has detected silicate clouds in the atmosphere of a brown dwarf, an object that bridges the gap between gas giant planets and stars. It has found unexpected chemistry in planetary atmospheres that theoretical models hadn't predicted. All of this establishes Webb as not just a promising instrument, but a genuinely transformative one that has already delivered science beyond what the design specifications guaranteed. The Alpha Centauri attempt sits within this context of demonstrated capability. The telescope has clearly shown it can characterize atmospheres and detect planets at distances of hundreds of light-years. The challenge at Alpha Centauri is not the telescope's sensitivity. It's the specific geometry of a bright binary system and the technical demands of coronagraphic imaging at small, angular separations. Those challenges are real, but they're engineering challenges, problems of technique and analysis, not fundamental physical limitations. And engineering challenges, in science, tend to yield to sustained effort and cleverness. Let's consider for a moment what happens to the scientific community's thinking about the nearest stellar neighbor if the planet is eventually confirmed. Not just in terms of the immediate detection, but in terms of the longer arc of what comes next. A confirmed Saturn-mass planet at Alpha Centauri A would immediately become one of the most intensively studied exoplanets in the catalogue. Not because it's particularly exotic, Saturn-mass gas giants are the most commonly directly imaged exoplanet type, because they're large and warm enough to be the most accessible, but because of where it is. Every follow-up technique would be aimed at it. Radial velocity observations would constrain its mass precisely, beyond just the lower limit that direct imaging provides. Additional Webb observations, now that the orbit would be known, would track it through its orbital arc. Spectroscopic observations would characterize its atmospheric composition. The presence of water vapor, methane, ammonia, phosphine, and other chemical species would be measured and compared to models of gas giant atmospheric chemistry. The planet's luminosity and temperature at different orbital positions would be measured, building up a thermal light curve that reveals the day-night temperature contrast and the nature of the planet's energy redistribution. If the planet has moons and a Saturn-mass object at that orbital distance might well have a substantial moon system, there would be attempts to detect those moons through various indirect means. The planet's orbit would be tracked precisely enough to look for the gravitational perturbations that any additional planets in the system would produce. Over years of observation, the full architecture of the Alpha Centauri, a planetary system, would begin to reveal itself. Not all at once, not easily, but piece by piece, through the accumulation of careful observations from multiple facilities working together. This is how scientific understanding of complex systems actually builds, not through single decisive measurements, but through the patient accumulation of complementary data from many angles. The Alpha Centauri system, if it has a confirmed planet, would become one of the most extensively observed planetary systems beyond our own. The scientific return from that investment would extend over decades. And if the Webb candidate turns out to be a false positive, then the story changes, but the scientific value doesn't disappear. A definitive non-detection established through the full suite of follow-up observations and independent analyses would be the most rigorous constraint ever placed on giant planet. Populations around Alpha Centauri A. If Webb's coronagraphic observations at the sensitivity level achieved in the current campaign cannot detect a planet, that tells you something concrete about what's not there. It places an upper limit on the mass and orbital distance of any planets in the observable parameter space. Those limits would be published, cited, and used by theorists to constrain planet formation models for this specific system. Future observation programs, potentially using a space telescope with even larger aperture and more advanced coronagraphic design than Webb would build on those limits to search deeper. The history of astronomy is full of examples where non-detections turned out to be as scientifically valuable as detections. The Michelson-Morley experiment, the famous 1887 null result that failed to detect the luminiferous ether, is the canonical example. A null result that didn't find what it was looking for, but found something far more important: the fact that light speed is constant, regardless of the direction of travel, which became a cornerstone of special relativity. The non-detection of certain radio signals from nearby stars, conducted by the Search for Extraterrestrial Intelligence programs since the 1960s, hasn't found what it was looking for. But it has established increasingly tight constraints on the prevalence and detectability of technological civilizations. Broadcasting radio signals, constraints that inform theoretical estimates of the Drake equation's parameters and the Fermi paradox's interpretation. A definitive non-detection at Alpha Centauri A would have a similar character. It would tell us something real and important about the system, not what we hope to find, but what's actually there. And that knowledge would be the foundation for everything that comes next. The specific calibration challenges at Alpha Centauri A deserve one more careful discussion, because they illuminate why this system is genuinely hard even for Webb. When a coronagraph blocks the central star, it's not perfect. Light leaks around the edges of the mask. Light diffracts around the mask boundaries. Light that entered the telescope on a path that put it at the edge of the primary mirror segment. Boundaries encounters a slightly different wavefront than light entering through the center of the past segments. All of these effects produce a characteristic diffraction pattern, a field of speckles in the region around the blocked star. Modern coronagraphic analysis attempts to characterize and remove this speckle pattern. The characterization is done either with a reference star observation, observing a similar bright star with the same instrument configuration and subtracting its speckle pattern, or with algorithms that model the speckle pattern directly from the science data. Both approaches have limitations. A reference star can never be perfectly matched to the science target in terms of brightness, color, distance, or the telescope's optical state during observation. Differences between target and reference produce residuals in the subtraction. Algorithmic speckle subtraction methods, like principal component analysis or non-negative matrix factorization approaches, extract the speckle pattern from the temporal behavior of the signal. Speckles evolve over time in a way that can be distinguished statistically from a real point source. These methods are powerful, but they can fail if the planet's signal contributes a non-negligible fraction of the total variance in the data. In that case, the algorithm might partially subtract the planet, along with the speckles, reducing the detected signal's significance. At Alpha Centauri, these challenges are compounded by the presence of Alpha Centauri B in the field. B is only slightly fainter than A. Its diffraction pattern extends into the field around A. To isolate A's diffraction pattern, you have to model B's contribution precisely. The model of B's contribution depends on accurate knowledge of B's position relative to A, B's brightness at the observing wavelength, and the instrument's response to B's light given its specific angular position in the coronagraphic field. Any error in any of these inputs leaves a structured residual. In the worst case, that residual mimics a planet. The team has been working to characterize B's contribution with increasing precision using dedicated calibration observations. But this is iterative work. Each round of observations improves the model, which improves the residual, which improves the sensitivity. The follow-up observations incorporate the improved model of B's contribution derived from analysis of the initial observations. This is part of why the follow-up is expected to be more definitive than the initial observations, not just because it uses the same technique applied a second time, but because the analysis benefits from everything learned in the first round. The question of what disturbing means in the context of the Webb Alpha Centauri result is worth addressing directly, because the answer is subtle. Nothing about a planet at Alpha Centauri A is disturbing in the sense of threatening or dangerous. A Saturn-mass gas giant 4 light-years away has no effect on Earth. It isn't capable of affecting Earth. What's disturbing, if that's the right word, is more epistemological than physical. It's disturbing in the sense of unsettling. It's unsettling because the nearest star system to our own might have a large planet, and we're not sure. It's unsettling because our best telescope produced a signal and then couldn't reproduce it. It's unsettling because the most intensively studied nearby stellar system in the history of astronomy is still keeping its deepest secrets from us, despite everything we've thrown at it. There's something philosophically uncomfortable about that. We live in an era where we've characterized the atmospheres of planets hundreds of light-years away, where we've detected gravitational waves from black hole mergers billions of light-years distant, where we've photographed the silhouette of a black hole at the center of a distant galaxy. And we genuinely don't know whether the star system right next door has a Saturn. That gap between what we can do at vast distances and what we can establish about our immediate stellar neighborhood is striking. It's a product of the specific technical challenges of bright, nearby binary targets, rather than any fundamental limitation on human knowledge. But it's real, and it's going to persist until the follow-up observations resolve the current ambiguity. In the meantime, the scientific community is doing what it should do, working the problem, applying the available tools, planning more and better observations, not overclaiming, not underclaiming, just trying, carefully and honestly, to figure out what's actually there. There's something that deserves to be said about what this episode reveals about the scientific process itself, and about the relationship between that process and the broader public understanding of how science works. Scientific results at the frontier are rarely delivered with the certainty that science is popularly imagined to produce. The public image of science is often one of definitive discoveries. A finding is made, it's confirmed, it's accepted, it becomes settled knowledge. The actual experience of working science, especially at the frontier of what's technically achievable, is much more complicated. Results are provisional. Follow-up sometimes confirms, sometimes complicates, and sometimes undermines the initial finding. The community debates interpretation. Different research groups analyze the same data and sometimes reach different conclusions. This is not a failure of science. It's how science works when the questions are genuinely hard and the measurements are genuinely at the edge of capability. The Alpha Centauri Webb result is a perfect example of science operating exactly as it should in this situation. A team with a new, powerful instrument pushes it at the most compelling nearby target. They find a signal. They report it carefully and honestly. They perform follow-up. The follow-up doesn't confirm the signal. They report the non-confirmation. They investigate the discrepancy. They plan more observations. They welcome independent analysis. At every step, the community's understanding of the system improves, even when no individual step delivers a clean, definitive answer. This is how hard science gets done. Slowly, iteratively, honestly, with more uncertainty at any given moment than the finished version of the story will contain. The finished version, whenever it arrives, will have a clear narrative. Either Alpha Centauri A has a Saturn-mass planet, or it doesn't. The Webb coronagraph detected it, or it didn't. But the process of getting to that clear narrative goes through exactly the complicated, uncertain territory that the field is currently navigating. There's a final dimension to the Webb Alpha Centauri result worth addressing, and it's one that rarely appears in standard scientific reporting. It concerns the relationship between instrument design and scientific ambition. The James Webb Space Telescope was designed over decades, argued for in budget cycles through the 1990s and 2000s, delayed repeatedly by technical challenges, and launched in December 2021, nearly 14 years behind the original launch target. Its design was optimized for specific science goals, observing the first galaxies that formed after the Big Bang, characterizing exoplanet atmospheres through transit spectroscopy, imaging the formation of planetary systems in nearby star-forming regions, and studying the chemical composition of objects throughout the solar system. Direct imaging of planets around nearby sun-like stars was not the primary driver of Webb's coronagraph design. The coronagraph was included in the mission, but the technical requirements were set primarily by science cases involving younger, more widely separated planetary systems where the contrast challenges are more forgiving. Applying the coronagraph to Alpha Centauri A is operating it in a regime the instrument wasn't optimized for. The angular separations are small. The target is extremely bright. The binary companion adds complications the design didn't specifically account for. This context matters because it explains both why the initial result was scientifically credible. The instrument is sensitive enough at this target to potentially detect a Saturn-mass planet, and why the follow-up non-confirmation isn't necessarily fatal to the planet's existence. Webb's coronagraph at Alpha Centauri A is being used at the margins of its designed capabilities. The fact that it produced a signal worth publishing is impressive. The fact that the signal didn't reproduce cleanly is consistent with operating at those margins. That tension between what the instrument was built for and what astronomers are asking it to do sits at the heart of everything that has happened at Alpha Centauri A since August 21st, 24. And it's precisely why what comes next matters so much. The calibration work being done now is worth describing in slightly more detail, because it represents the state-of-the-art in a technique that will be critical to exoplanet science for decades. Reference differential imaging. The approach of subtracting a reference star's diffraction pattern from the science target's image has been refined substantially in the era of space-based coronagraphs. The key insight driving current improvements is that the speckle pattern produced by a coronagraph is not random. It's deterministic, arising from specific physical causes. The shape of the primary mirror, the alignment of the secondary, the figure errors on the individual mirror segments, and the thermal state of the telescope structure. If you can accurately model the physical causes of the speckle pattern, you can predict what the speckle pattern looks like at any given time. And if you can predict the speckle pattern, you can subtract it more accurately than any reference star observation allows. Because a reference star always introduces its own differences from the science target. This physics-based approach to speckle modeling is being actively developed for Webb and for future telescopes. It uses the fact that Webb's wavefront sensing system continuously monitors the shapes of its mirror segments and the alignment of the overall optical system. Those measurements can be fed into optical models that predict the coronagraphic point spread function, the detailed shape of the diffraction pattern, to a level of accuracy limited primarily by how well the optical model captures the telescope's real behavior. The Alpha Centauri observations are contributing to the development of these models. Every observation of this bright, well-understood target provides calibration data for the instrument models. Every attempt to subtract the stellar diffraction pattern reveals discrepancies between the model and reality, discrepancies that, when understood, improve the model for future use. This cumulative improvement in the analysis tools is part of what makes each round of Alpha Centauri observations valuable even when the planet is not confirmed. The telescope is being understood better. The techniques are being refined. The limiting factors are being identified. That knowledge benefits not just Alpha Centauri science, but every other high-contrast imaging program that Webb will conduct over its planned lifetime. Webb was designed to operate for at least 10 years after launch, with a goal of 20 years if propellant and instrument health allow. The Alpha Centauri observations being conducted now are early in that operational window. Whatever is learned from this campaign will inform observations of this system for years to come. And the Alpha Centauri system, being the closest, brightest, and most historically significant stellar neighbor we have, will almost certainly remain a priority target throughout Webb's operational life. If the planet is confirmed, follow-up characterization will occupy multiple observing cycles. If it isn't confirmed, the question of what's actually there will remain open and scientifically compelling enough to motivate continued deep observations. Either way, Alpha Centauri A and the James Webb Space Telescope are going to have a long scientific relationship. Tonight's story is the beginning of that relationship, not its conclusion. The stars over the southern hemisphere are burning tonight, as they have for billions of years. Alpha Centauri A and B, from Earth's perspective, appear as a single bright star, the third brightest star in the entire night sky, with the brighter component, Alpha Centauri A, formerly named Rigil Kentaurus, a name meaning foot of the centaur in Arabic. Only from very dark skies or through a small telescope can you resolve the two stars separately. That single point of light contains, around one of its two stars, a mystery that the most powerful space telescope ever built has encountered and not yet fully resolved. That's the state of things. Not everything is answered. Not every mystery yields to the first attempt. But the attempt has been made with tools worthy of the question, and the next attempts are being designed with everything learned from this one. The history of how we've come to understand the planets in our own solar system is instructive here. It took centuries of increasingly precise observations, multiple failed theories, and the gradual accumulation of careful data to build the picture we now take for granted. The history of how we've come to understand the planets orbiting other stars is only a few decades old, and the technique of direct imaging that Webb is applying at Alpha Centauri is even younger than that. We are early in this story. What feels like an unsatisfying non-confirmation today may, in retrospect, be remembered as the observation that first established that the technique works at Alpha Centauri, that it can produce signals at the required sensitivity level, even if the first candidate didn't hold up. The next time around, with the lessons of this campaign incorporated into the design, the result may be definitive, in one direction or the other. And definitive, in science, is what matters. The stars look exactly the same tonight as they did before Webb turned its mirror toward Alpha Centauri A. That warm, bright point of light in the southern sky gives no visible sign of the extraordinary scrutiny being directed at its surrounding space. No indication of the data files being analyzed, the simulations being run, the instrument models being refined. The independent teams working through the same numbers from different directions. But for the first time in the history of astronomy, we have an instrument that can actually look for planets around Alpha Centauri A with sufficient sensitivity to potentially find them. Not through inference. Not through statistical analysis of a star's wobble or dimming. By searching directly in the infrared for a planet's own thermal glow. That's a genuinely new capability. The fact that the first attempt produced a result that hasn't yet been confirmed, that the answer isn't yet clear, that more work is required, none of that diminishes how significant the capability itself is. It's the closest possible target. It's the best available instrument. And the result, whatever it ultimately turns out to be, will be the product of the most careful, most technically capable search for planets around Alpha Centauri that has ever been conducted. 2. The follow-up observations will be completed. The analysis will be published. The community will reach a conclusion, and that conclusion will face scrutiny, and it will either be accepted or challenged on its merits, as every scientific result should be. All of that is in motion right now. And whenever the answer arrives, months from now, perhaps a year or two, it will be one of the most consequential results in the history of planetary science. Because this isn't just any star, it's the star next door. And we're finally looking at it with tools worthy of the question. Thanks for spending this time with me tonight. The Alpha Centauri story is still being written, and the next chapter may come sooner than most people expect. If this kind of deep look at what's really happening at the edge of human knowledge is what you come here for, a like or a subscribe helps this channel keep making exactly this kind of content. Good night.